Welcome to the second lecture on cardinality. So here I shall start with the Cantor's theorem. So it says for any set A, the cardinality of A is strictly less than the cardinality of the power set of A. So what is a power set of A? So let A be a set, then the power set of A is the collection of all subsets of A, and it is denoted by just P of A. Fine. So here is some example. That's mean if your A is just the empty set, then the power set of PA is the set which contains the empty set only. Now if A is singleton, say singleton of A, then P of A is the collection of the empty set and the whole set A. If A is the set AB, then PA is the collection of the sets empty set, singleton A, singleton B, singleton AB. So in this way. Fine. Now this theorem says that the cardinality of A is strictly less than the power set of A. That is the cardinality of the power set of A. Okay. So here is the proof. So first of all, we can define a injective function. So let us define a function f from A to power set of A by f of A is singleton A. Then it is easy to see that f is a injective function. So then f is an injective function, right? So therefore the cardinality of A is less than equal to the cardinality of the set P of A. Okay. Now we claim that cardinality of A is strictly less than the cardinality of P of A. That's mean now we claim that this strictly less than the cardinality of P of A. That is there is no bijection from A to P of A. Okay. So first we will assume that there is a bijection and we will get a contradiction. So let, if possible, let H A to P A be a bijection or bijective function. Okay. Then for each a, what is h of a? So h of a is a subset of a, right? So h of a is a subset of a. Now we define a set. So let S is the set which is defined by all of the collection of the element of A such that A not in H of A. Now obviously S is a subset of A, right? That's mean since S is a subset of A, that's mean S belongs to power set of A. Now it is given that H A to P of A is a bijective function, right? Now since H A to P of A is a bijective function, so there exists a x in A such that h of x equal to S, right? Now what is my x? X is an element of A and a subset of A. Here x belongs to A and S is a subset of A, right? So therefore we have two possibilities for the element x. So either x belongs to S or x belongs to S complement. That's mean, so thus we have two possibilities. So one is x can be in S or the other possibility is x is not in S. That's mean x belongs to that A minus S, right? So these are only two possibilities. Now we can look at the first possibility, that is case 1. So if x belongs to S, now what is my S? S is the collection of all the elements of A such that A not belongs to H of A, right? Now that's mean x not belongs to H of x, right? Why? See, x belongs to S and S is the collection of all the element such that A not belongs to HA, right? Now since x in X, therefore x not belongs to H of x. Now what is my H of x? Now we know that H of x is S. So this is S. So this is a contradiction. That implies x not belongs to S. So we assume that x in S and we get x not belongs to S. So this is a contradiction. Right? Now we can look at the second case. Now here is my case 2. So x not in S. Okay, that's mean x belongs to A minus S. Now what do you mean by x not in X? That's mean x not belongs to, what is my S? S is just Hx. and also x belongs to A, right? So that implies x belongs to A and x not belongs to h of x, right? Now what is my definition of S? Recall that this S is the collection of all of these sets, all of these the elements of A such that A is not in H of A. Now since x satisfies this, that's mean x belongs to S. But we assume that x not in S, right? So this is again a contradiction. Therefore, if we assume x belongs to S, then we get a contradiction, right? And if we assume x not in S, then again we get a contradiction. Therefore, this may not happen. That implies thus H A to P of A must not be a bijection. So therefore there is no bijection from A to P of A. So that implies the cardinality of A is strictly less than the cardinality of P of A. Fine. Therefore, the cardinality of n is strictly less than the cardinality of the power set of n. Fine. Now we prove that the cardinality of the power set of n is 2 to the power of the cardinality of n. Okay. Now first we denote this set. That's mean the set 0 1 power n denote the set of all functions f from n to the set 0 1. That is 2 element set. Okay. Now we can think this set the set this as a collection of all sequences with entries 0 and 1, right? And we have already seen that the collection of all the sequences with the entry 0 1 is uncountable, right? So in that case we can easily prove that this set, that is the 2 element set and the power n, that is the set of all functions from n to the 2 element set, is also uncountable, right? Anyway, so now we have this lemma. So we prove that the cardinality of power set of n is same as 2 to the power this. Okay. Or in other words, we will prove that there is a bijection H from the set Pn to this collection of functions f from n to 0 1. Okay. Now here is the proof. So first of all, let A subset of n, that is A is a subset of natural number. Okay. Now define a function say chi A from the natural number n to the set 0 1 by this way. So chi of A, so this set when n belongs to A, then the value is 1. You can write here if and the value is 0 if n not in A. Okay. Now we define a function. So let h p n to the set this be a function defined by this way. So h of A will be chi of A. So we know, so from this we know that chi A belongs to that set, right? So chi A is a function from natural number to the set 0 and 1, right? Now here we define a function h from the power set of A to the set of all functions f, where f is a function from n to 0 1, right? So we define in this way that h of A equal to chi of A, right? So this is a well defined function. Now we prove that this h is injective. Now why h is injective? So first of all, so let A be subset of Pn, so belongs to Pn, we can say here, right? And let say chi of A is same as chi of B. Okay, that imply chi of A n is same as chi of n, sorry, chi of B n for all n belongs to natural number, right? Therefore we have chi of A n is 1 if and only chi of B n is 1, right? Now this will imply that A equal to B. Why? So if A not equal to B, then there exists n belongs to A such that n not belongs to B, or there exists n belongs to B such that n does not belongs to A. That is the reason these sets are not equal, right? But in both of these cases, so we can write this is M chi of M, sorry, chi of AM is not equal to chi of BM, and because one of them will be 1 and one of them will be 0. Now this is a contradiction, right? So therefore So therefore A should be equal to B. That implies H is injective. Fine. Okay. Now we shall prove that H is surjective as well. Now first of all, we assume one point, say G, belongs to this set. That's mean G is a function from n to 0, 1. Now let S equal to G inverse singleton 1. Okay. Now that imply G of n will be 1 if n belongs to S and equal to 0 if n belongs to, so not belongs to S, right? And what is my chi of S? Now chi of S is a function from n to 0, 1 and chi of S n equal to 0 if n belongs to S, sorry, it is 1, and equal to 0 if n not belongs to S, right? Therefore G is equal to chi of S. So thus H of S equal to chi of S equal to G. And here from this we can easily see that this is a subset of n, right? So therefore H is surjective. So thus we have H is a bijection done, and therefore the cardinality of power set of n is same as the cardinality of this set. So the two element set and power n, right? And this is just 2 to the power this n. So we are done. Now we have the next result. It says the cardinality of this set is same as the cardinality of the set closed interval 0, 1. And if we can prove this one, that's when we can say that the cardinality of the set closed interval 0, 1 is same as the cardinality of the power set of n. Okay. Now first we recall that the binary representation of 0, 1. This set. Okay. So we know that any element x belongs to 0, 1. So we will say that in decimal, right, can be represented as x equal to this one, summation n equal to 1 to infinity sum b n by 2 to the power n. where Bn belongs to either 0 or 1 for all n. And in this case, the binary representation of x is 0.b1, b2, b3, b4 in this way. Okay, so this is just binary representation of real numbers, or in particular the binary representation of a point in the set closed interval 0, 1. Fine. Now this presentation, that is the binary representation, is not unique for countable cases. In fact, if you have decimal representation of a number, then also it is not unique for countable number of cases. Why? So here just note that the binary representation is not unique for countable cases. You can prove that, because if say Bm equal to 1 and Bn equal to 0 for all n bigger than m, then the same element has also a representation Bm equal to 0 and Bn equal to 1 for all n bigger than m. So for example, if you have 0.1, right, then 0.1 is same as 0.011111 in this way, in binary representation. Now similarly, suppose you have a number 0.1011. Now since it stops somewhere, then we can, so sorry, it is 0.101. Now it stops here, right? So in that position we can put 0, and then we can remaining position we can put just 1111 in this way. That's mean whenever you have a presentation which stops somewhere, then we can make it infinite. Even we can do in the decimal as well, right? Suppose you have 1, then we can write 1 as 0.99999. Suppose you have 0.3. Now 0.3 can be written as 0.299999 in this way, right? So therefore, if you have a number, in, or you can see, if you have a real number in closed interval 0, 1, then there are countable numbers which has exactly 2 representation and the other one has single representation. Fine. Now here we have the proof of this theorem. So let f belongs to this set. That's mean f is a function from n to 0, 1, right? Now define a function f from this collection of functions to the real number of 0 and 1 by So summation n equal to 1 to infinity f of n by 2 to the power n. Okay, so here obviously it is in decimal sense. Okay, now by the construction f is surjective. Why f is surjective? So first of all, so why this is surjective? Okay, so first of all, we assume a number x from open close interval 0 1. Now that implies we know that it can be written as summation I equal to 1 to infinity bi 2 to the power I, where I bi belongs to 0 and 1. Now obviously it is in decimal sense, right? We know that this is the property of real line. Now then, so let f into 0 1 be a function such that f of I equal to bi for all I belongs to natural number. Now that implies capital F of the small f will be my x, will be that expression which is same as bn by 2 to the power n. This is my x, right? So therefore f is surjective. Now can you say that f is injective? See, now note that f is not injective because we can choose two functions which has the same representation, right? So that will converge to a same number. But the problem is that here the number which makes this problem, that is the number for which this function is not injective, the problematic points are only countable one, right? Because only we have only countable number of points which has exactly two representation. Now if we delete so countable number of points from the left hand side, then still the cardinality will be the same as before, and then we can make a bijection. Okay, so in this way we can find a bijection from this set to this set. So in this case we can roughly say that this function is almost bijection. So this is not a bijection, but if we delete the countable numbers from the left hand side, then it will be a bijection. So we can say it is a almost bijection. So anyway, so I will prove it directly that this cardinality of this and cardinality of this will be same. So anyway, so in this case we prove that we have a function f from this set to this set which is surjective, right? So therefore now since f is surjective, so the cardinality of this set is bigger or equal to cardinality of 0 1, right? Now define a set G from closed interval 0 1 sorry, the set 0 1 power n to the set closed interval 0 1. Okay, in this way should be defined by this g equal to summation n equal to 1 to infinity g of n by 10 to the power n. Now observe that here if g1 is not equal to g2, okay, that imply their image should be different, right? This is also property of real number. Why? Because what is this set here in decimal sense here. So here since g1 not equal to g2, that imply there exists n such that g1n is not equal to g2n, right? Now g of g1 and g of g2 are decimal representation with entries 0 and 1. Remember that it is decimal representation with the entry 0 and 1. Now since g1n is not equal to g2n, that imply the nth position, so we can say that in the nth position of g of g1 and g of g2 we have different numbers, that is one of them will be 0 and other one will be 1, right? So therefore g of this is not equal to g of g2. So here g is injective. Now since we have a injective function from the set 0 1 power n to closed interval 0 1, therefore the cardinality of this is less than equal to cardinality of 0 1. So suppose this is 1 and this is 2. So by 1 and 2 we have this cardinality is same as the cardinality of the closed interval 0 1, right? So we are done. Now here I just want to make one note on this. So why this is surjective and how we can make it bijective. So here f is not bijective because, so let my set S equal to 1 and T equal to 2, 3, 4, this one. Okay, then we have chi of S and chi of T. We have these two functions, right, in that set. right? Now if we take f of that chi of s, so that will be, see, summation n equal to 1 to infinity, so chi of s n by 2 to the power n, right? Now here it will be just 1 by 2, that is 0.5, obviously in decimal. Now what will be my f of chi of t? This will be summation again n equal to 1 to infinity chi of t n by 2 to the power n. So this will be 1 by 4 plus 1 by 8 plus 1 by 16 in this way, that infinite series. Again if you take the summation it will be half, that is 0.5. So we have two these distinct point, that is distinct function whose image are same. So that imply f is not bijective, or you can say is not injective, right? But we can refine the function and the domain and we can make it bijective. How? Now since only countable values say elements of 0 1 have double expressions, so we can remove the corresponding values or functions from left and so since we are deleting only countable values from the left, so therefore the cardinality will be the same as before, and then we can prove that this. Okay, so in that case you can directly find the bijection. Now we have a remark. Okay, so the remark says the cardinality of closed interval 0 1 is same as the cardinality of R. Why? We know that closed interval 0 1 is subset of R. Now since this is a subset of R, so we can give a inclusion function, right, and that is injective. Therefore we can easily say that the cardinality of closed interval 0 1 is less than equal to the cardinality of R, right? Now again we have a function f from open interval 0 1 to R by, we can define by f of x equal to x minus half by x minus 1. Now you can easily check that f is a bijection. In fact, if you know the continuity, you can easily check that this f is a homeomorphism. Okay, now since it is a bijection, therefore that cardinality of open 0 1 is same as the cardinality of R, right? Therefore we can say that cardinality of R is same as open interval 0 1, the cardinality of this, again open interval 0 1 is subset of closed interval 0 1, so its cardinality is less than this. Now this is my 1 and this is my 2, so by 1 and 2 we have that closed interval 0 1, the cardinality of this is same as R. So we have, if we attach all of the theorems, then we will have cardinality of R is same as cardinality of also irrational number R minus Q, right? And it is the same as the cardinality of this set, and it is the same as the cardinality of P of n, right? And we know that since R is uncountable, so cardinality of natural number is strictly less than cardinality of R. We also know that cardinality of n is strictly less than the cardinality of its power set, right? So it should be less than R. Now the question is there any other set we have a question, right? So this leads to a question that is there any other sets, say A, such that cardinality of n is less than cardinality of A less than cardinality of R. Now what is the answer of this question? Actually one cannot give the answer. So there is a continuum hypothesis. So we have one continuum hypothesis. So what is this hypothesis? It says there is no set whose cardinality is strictly between the cardinality of n and the cardinality of R. So this is a hypothesis. Now what about the proof of this hypothesis? Now it is now known that continuum hypothesis cannot be proved. And one also proved that this hypothesis cannot be disproved as well. So this is one such hypothesis which cannot be proved and which cannot be disproved. So we assume this hypothesis as an axiom. Now cardinality of n is strictly less than the cardinality of the power set of n, right, which is same as the cardinality of R, and this is, we know, 2 to the power cardinality of n, right? Again we know that cardinality of r is again strictly less than the cardinality of p of r. Now similarly one can prove that this is same as 2 to the power cardinality of r, and so on in this way. And generally this one is denoted by LF naught, this is denoted by LF1, this is denoted by LF2, and so on. Fine. So now I shall prove one interesting problem. So what is the cardinality of the collection of all continuous functions from R to R? Okay, so here is the proof. So here we use the fact that cardinality of R is same as cardinality of 2 to the power cardinality of n, and cardinality of Q, that is set of rational number, is same as cardinality of n, and it is same as the cardinality of n product n. Okay. Now first of all, let x equal to set of all functions such that f is a functions from R to R, and f is actually constant function, so such that f is defined by fx, f of x equal to c, where c belongs to real number, right? So x is the collection of all constant functions only. Obviously we know that constant function is continuous, and y is the collection of the given one, that is the collection of all continuous functions from R to R. So here my y is all the functions f such that f is a functions from R to R and continuous, right? And we denote another collection of functions f such that f is just a function from Q to R. Okay, so this is my these three sets. So x is the collection of all constant functions, we know this is continuous, right? And y is the collection of all the functions, that is all the continuous functions from R to R, and z is the collection of only functions, we are not taking the continuity, so z is the collection of only functions from Q to R. Okay, now we know that any continuous function f from R to R can be, or we can say directly is, uniquely determined by its values in Q. Why? So let x be an arbitrary element in R, right? Now since Q is dense in R, so since Q is dense in R, so there exists a sequence Rn which is in Q such that Rn converges to X, right? Now given that f is continuous at X, so since f is continuous at X, so by using the definition of continuity we have f of Rn converges to f of X. Therefore, if you know the values of f of Rn, then you will know the values of fx. Therefore, the value f of x is uniquely determined by the values of f of Rn. That's mean if you know the values of the function on rational numbers, then you know the values of the function in each point of real numbers, right? Since f is continuous. Now what is my z? Z is the function of which is any function from Q to R. That's mean we have y subset of z, right? So z is any function from Q to R, and y is a collection of function which can be obtained from some functions which is from Q to R, right? So y subset of z. Now also we know that its constant function is continuous, right? Therefore, x subset of y. Why? Because x is the collection of constant functions only, and y is the collection of all the continuous functions from R to R, right? So y subset of x subset of y. Now what is my cardinality of x? Now cardinality of x is just the cardinality of R, right? Because for each values in R we get a constant function, and these are all, right? So the cardinality of x is exactly the cardinality of R. Now what is my cardinality of z? Now what is z? Z is a collection of all the functions from Q to R. Therefore its cardinality is R power Q, right, which is same as R power cardinality of Q. So cardinality of R power cardinality of Q, right? But we know that cardinality of Q is same as cardinality of N. So it is cardinality of R power cardinality of N, right? But we know that cardinality of R is 2 to the power cardinality of N. So it is 2 this into this. That's mean it is 2 to the power cardinality of N into cardinality of N, and again it is same as cardinality of N cross N, which is same as cardinality of N So that is cardinality of R. Right? Since we have X subset of Y subset of Z, that imply cardinality of X less than equal to cardinality of Y less than equal to cardinality of Z. Right? And we know that, so we have proved that cardinality of X is cardinality of R, so it is less than equal to cardinality of Y, again it is less than equal to cardinality of R. Therefore cardinality of Y is same as cardinality of R. Right? So therefore the cardinality of the collection of all continuous function from R to R is the same as the cardinality of R. Fine. So in this way you can solve many problems, but here I just want to solve one more problem. Say this one, say problem 2. That cardinality of R is same as cardinality of R cross R. Okay. First of all, observe that we have a bijection. So there is a bijection, open interval 0 1 to R. Right? We have shown the bijection, so we can write again. So x going to x minus half by x into x minus 1, this one, right? So this is a bijection from closed interval 0 1, sorry, open interval 0 1 to R. Now if we have suppose two bijections, say f from A to B and say G, say some C to D, say both are bijections. Now that imply if we just take the multiplication, then that Cartesian product of this C to B cross D, this is also will be a bijection. Right? So that's mean, so here we just first prove that cardinality of 0 1 cross 0 1 is less than equal to cardinality of 0 1, and then the proof will follow. Okay. So now there is a bijection, sorry, injection from F 0 1 cross 0 1 to open interval 0 1. So we define a map F by 0.A1, A2, A3, this comma 0.B1, B2, B3 in this way to 0.A1, B1, A2, B2 in this way. Okay. So one can easily check that f is an injective function. Therefore this, so we have the cardinality of 0 1 cross 0 1 is less than equal to cardinality of 0 1, and we know this is R, right? And again we know this is the cardinality of R cross R. So we have this one. On the other hand, cardinality of R is same as cardinality of R cross 0, and that is less than equal to cardinality of R cross R, since R cross 0 is subset of R cross R, right? So therefore we have cardinality of R is same as cardinality of R cross R. Now similarly one can prove that cardinality of R is same as cardinality of R, that is n times of R. Okay, so these are all about for today, so I will stop here.